Hi, and welcome back to the wonderful world of the scientific hypothesis. My name is Brad Alger, and in this video, we're going to return to and extend the general concept of different kinds of science. Besides basic and applied science, which we've already reviewed, there are several more distinctions that we need to make. In fact, some people will argue that because there are other ways of going about science, the hypothesis no longer has a place in today's science. This mistaken idea is based on several misconceptions, as you'll see. I'll describe 4 of the most prominent alternatives to hypothesis-based science and explain how we're not really forced to choose among them. Rather, the different kinds come into play at different stages of an investigation, and they interact and coexist quite productively for the most part. It is true that big data, in one sense, big data may be an outlier in this case, but I'll explain that as well. So these other kinds or modes of science that have been proposed as alternatives to the hypothesis include discovery science, open-ended questioning, computational systems, and big data. We'll describe each one of these, define them, and discuss their relationships to the hypothesis along the way. To begin with discovery science, this is the approach in which individuals collect, classify, and characterize elements in a large field, a large data set. For example, the Human Genome Project, characterizing the gut microbiome, the flora and fauna in our intestines. There have been projects to characterize all of the gases in Earth's atmosphere, and so on. The goal of a discovery science project is completeness. It tries to identify all of the elements and their interactions. It isn't specifically intended to explain anything or solve a particular problem. It does provide raw material for hypothesis testing, however, and it does not require any prior hypothesis to undertake a discovery science project. Now, another alternative is the idea of open-ended questioning. And this is where one begins with some question about nature and then asks a series of questions about it. And each answer to these questions may lead to further questions. It is, by definition, an unstructured project. There's no specific path or particular objective. It does, again, provide the raw material for hypothesis testing, but it does not require a hypothesis itself. Next, let's look at what's been called computational or system science. This is the approach that's taken when, in a large complex system, properties of the system emerge that are not predictable from the study of any of its individual parts or their interactions. The classic example is the traffic jam on the highway, whereby large numbers of cars begin slowing down, they may be even stopping entirely, gridlock can ensue, and yet no amount of study of individual drivers or cars can predict the occurrence of traffic jams. Rather, this is something that emerges as a property of the complex system as a whole. And therefore, the computational approach is to insert the properties, the known properties of the individuals and the elements and their interactions into large computer models and try to model the system with the idea of trying to predict and understand the occurrence of, let's say, traffic jams. The computer model, in other words, essentially serves as a hypothesis. And finally, we come to the concept of big data, which really is a very different approach to science. The data sets involved in big data are indeed very, very large, and they're generally very messy. They're not curated or tended or ordered the way many data sets are. A classic example is from the search engine Google, which handles up to 70,000 searches per second, which translates into many billion per day and a couple of trillion per year. This is the idea of big data. Now, the data in this approach are handled generally with massive computer processing, and it uses algorithms to look for correlations within these giant data sets. Now, the correlations themselves are enormously complex. When you have a data set that might range up to 10 to the 15th elements with uncountable numbers of interactions, then the best one can hope for, it is thought by many big data scientists, is to find some kind of n-dimensional correlations within the data set that'll somehow prove to be useful. An example was the development of the Google Flu Trends model, which attempted to look at all of the data from millions and billions of its searches to try to find correlations that would reliably predict the onset of seasonal flu. Now, this approach eventually failed, but it was an early attempt to replace hypotheses, that is, the actual understanding of why flu occurred, with information gained from simply these large correlations. So the example of the big data mindset is that correlations actually will replace hypotheses in future science. Now, this isn't always true nowadays, and big data has been used in the sense of the computational and systems approach we talked about earlier to develop models which are more or less conventional hypotheses. And finally, big data can serve as the raw material for truly conventional science. Nevertheless, big data represents an approach that is going to expand in the future with unknown influences on the hypothesis and conventional science. So, just to review these different kinds or modes of science and their relationships to the scientific hypothesis, we start with discovery science and open-ended questioning. And as we saw, these are really steps that precede the development of conventional scientific hypotheses, but they don't really replace it. The computational systems approach is really more of the same. It is another way of developing a hypothesis, which is often called a computational model to understand a large data set, and yet the model itself makes predictions and can be tested as a hypothesis can. And finally, we come to big data, which has a very complex series of relationships. Big data may be used in the context of leading up to and testing conventional hypotheses. It may generate a model, which, as we've said, is more or less the same as a hypothesis. But finally, there is this unusual concept of the big data mindset, in which correlations among these enormous data sets are fundamentally ungraspable, not understandable by the human mind, and therefore the notion of a hypothesis as an explanation entirely vanishes, and the correlation completely takes the place of a hypothesis. The bottom line at the moment is that not all scientific modes involve prior hypotheses, and that doesn't mean that we have to get rid of the hypothesis, because the various modes are not mutually exclusive. In fact, they interdigitate quite nicely with the hypothesis, and scientists transition smoothly back and forth among the different modes. Hypotheses are needed, however, when data call for explanations, and that is whether one starts with discovery science and so on, that when an explanation is actually called for is when the scientific hypothesis is brought to bear. Thanks for watching. Remember to give it a thumbs up if you like it and subscribe to hear more. See you next time.